All right, this one's a doozy. We have a farmer, he's growing rice and lentils, and the amounts of rice and lentils that he's creating are distributed randomly across this what's called a joint distribution. We don't know how much rice he's going to make or how many lentils he's going to grow, but it'll be a random variable, and the likelihood of each of those events are given by this table. The first thing we want to figure out is the expected rice crop. So the expected rice crop would be E of x, because x is rice and y is lentils. In order to do that, we need to create a marginal distribution table. So the marginal distribution is a little baby table. Let's do this in pink. Little baby table with the x values and the associated probabilities of all those x values. So looking at the top, all the possible x values are 400, 500, and 600. In order to get the values here, we just sum across the column underneath each of those x values. So 400's x value, or the x value of 400, has these as its corresponding probabilities, and when I add them up, I get 0.3. When I do it for the 500 column, I get 0.4. And when I do it for the 600 column, I get 0.3. Because we're probably going to need it at some point in the future, I'm going to do the same thing, but for y. So let's go ahead and get the y marginal distribution. The possible y values are 200, 300, and 400. So I'm going to put those here, 200, 300, and 400. And in the same fashion, I'm going to add across the row corresponding to each y value to get the corresponding probabilities. This so happens to be 0.3, 0.4, and 0.3. Now, I don't want you to come away thinking that this is always going to happen. It's just so happened that these numbers were chosen in such a way that 0.3, 0.4, and 0.3 were the probabilities for both tables, and that was just a coincidence. It doesn't always happen that way. All right. Next step is to figure out the expected rice crop, and that's as simple as doing the following. We are going to say E of x equals 400 times 0.3, 500 times 0.4, plus 600 times 0.3. And this comes out to be 500. To get variance, well, actually, it doesn't ask for variance immediately, but we are going to have to get variance at some point because we're just going to need it later, trust me. We're going to get variance, but in order to do that, we need to get our hands on E of x squared. E of x squared is the same exact calculation as we did before, but with each of these x values being squared. So instead of 400, it's 400 squared times 0.3, plus 500 squared times 0.4, plus 600 squared times 0.3, and this comes out to be, if I'm not mistaken, 256,000. That's a big number. And then in order to get variance, variance is obtained by taking E of x squared, which was 256,000, and subtracting this 500 squared. I should say 500 squared. So 256,000 minus that number squared gives me 6,000. So my variance of x is equal to 6,000. I'm going to do the same exact thing for y. Before I do that, I'm going to kind of create a table that kind of puts all these values together. So we have E of x, we just found to be 500. V of x, we just found to be 6,000. We are going to use these in a minute. Okay, let's go ahead and do the expected value of y. Okay, now that I have variance of y and expected all this stuff, I can go ahead and put E of y equals 300. And V of y also equals 6,000. Okay, all those values, got them all. Cool, great, put them off to the side. Now, we've already answered the question about what the expected rice crop is, but now we want to answer a question about what is the rice crop when the lentil crop is 200. So when I say x given lentil crop is 200, or when I say expected value of x given y is equal to 200, I'm now only looking at the row of the joint distribution that corresponds to y equals 200. So now I'm going to recreate this marginal distribution, or rather, it's no longer called a marginal distribution, it's called a conditional distribution, since it's conditioned on the fact that y equals 200. And the associated probabilities for those are 0.2, or actually, let's go ahead and put the x values, 400, 500, 600, and 0.2, 0.05, and 0.05. The problem with this is these values don't sum to 1. So if I don't add up to 1, these are all supposed to add up to 1 in order for this to be a distribution, but it doesn't. So how do we fix that problem? What we need to do is we need to scale each of these numbers by their sum, which is to say this sum actually equals, let's back this up a little bit. This sum, if I add these numbers up, actually equals 0.3. And that's the problem, is that that doesn't equal 1. So we're going to divide each of these numbers by 0.3 so as to make it correct. So let's say divided by 0.3, divided by 0.3, divided by 0.3. And now these probabilities, if you grab a calculator and add this to this, you will get 1. So this is now a correct distribution. And from here, I can go ahead and compute the expected value of x the way I normally do, which is to say I say 400 times this number plus 500 times this number, this ends up being 1/6. And 600 times this number, this also ends up being 1/6. So this all comes out to be 450. So that is the expected value of x given y equals 200. Okay, now we're going to do covariance. Covariance requires we have e of xy minus e of x times e of y. Now the good thing about this is we already found e of x and e of y earlier, so we're going to take those values and put them right here, right now. That's going to give me 500 times 300. But what about this e of xy term? Well, this is the annoying part. This e of xy term is obtained by doing the following. We pick one of these probabilities. Let's say we'll start with 0.2. And we're going to multiply this probability by not just the 400, but also the 200. So we're going to say 400 times 200 and multiply it by 0.2. So we're going to say e of xy equals 400 times 200 times 0.2. And then we do it again, but for this probability. So 500 times 200 times 0.5, or 0.05. And then we keep going. We 600 times 200 times 0.05. We're going to do this for every single probability value inside this table. Now this all adds up to be 1,500, or 153,000, period. That's it. That is your e of xy. So this value can go up in here. I'm going to take 153,000 and put it right here. So that now 153,000 minus 500 times 300 will just come out to be 3,000. This is great. I'm going to take this value and put it as part of my chart. So covariance of x and y equals 3,000. Is it independent? Well, easy enough. They're independent. This is not equal to 0, so they're not independent. We know for a fact that anytime the covariance is not equal to 0, they're not independent. So not independent. All right, now we need to create a function for the farmer's income. We're told that rice counts for $2 a pound, but he's got to feed his family 200 pounds of those, 200 pounds of rice. Furthermore, lentils cost $3 a pound, but he also has to feed 100 pounds of the lentils to his family. So this ends up being his income. He doesn't see the benefit, or at least the monetary benefit, from those 200 pounds of rice that he and his family consume, nor does he see the economic benefit from the 100 pounds of lentils that he consumes because, well, they're in his family's belly, so probably not selling them. All right, so this ends up being z equals 2x plus 3y minus 700. This will allow us now to create the expected value of z and the variance of z. I'm going to take the expected value of both sides. The expected value of the sum is the sum of the expected values. So I can write this as e of 2x plus the expected value of 3y plus the expected value of negative 700. One thing to remember for absolute, or not absolute value, but expected value is you can take out any constant coefficient on those y's. So what we end up with is 2 times e of x plus 3 times e of y. And the expected value of a constant is just that constant. So we just get minus 700. Using the values from over here, we have e of x is 500, e of y is 300. So we get 2 times 500 plus 3 times 300 minus 700, which ends up equaling 1,000 plus 1,900 minus 700 is 1,200. And that is the expected value of his income. All right, now we need to create the variance of his income. I probably shouldn't have erased the equation that tells us what his income is. So that's 2x plus 3y minus 700. Variance of z equals variance of 2x plus 3y minus 700. So here's the tricky part. Anytime you have two random variables in a variance, you can separate them, but you have to throw in a covariance term. So here's what this looks like. We can say variance of 2x plus variance of 3y, but then we have to say 2 times the covariance of 2x comma 3y. The nice thing about constants by themselves inside a variance is that they just vanish. So this negative 700, poof, gone. All right, how do we deal with this? Well, let's do a different color again. Any constant coefficient of an x can come out in front, but you have to square it. So this is going to become 3 squared, and this has become 2 squared, giving me, oh, by the way, over here as well, these guys can come out, but you don't need to square. So don't square these guys. They just come out like normal. Okay, so what we end up with is, back to blue, we end up with is 4 variance of x plus 9 variance of y plus 2 times 2 times 3 is 12 covariance of x comma y. These are all values we have in the table off to the left. So we have 4 times 6,000 plus 9 times 6,000 plus 12 times 3,000. And this all comes out to be 114,000 even.